All right, so we're ready to start back. So I'll introduce Professor Eric Chittimbar. So Professor Chittimbar, this is his second year now at Illinois, and so he's an expert in quantum information. So we have him teaching about signals, which is unrelated to quantum.
Thank you very much, Linford. It's awesome to be here and talking to you all. Actually, one can make an argument that there is a connection between quantum information and signal processing. In fact, one of the things we're talking about today is something known as a Fourier Transform. In fact, there's a quantum version of that, and it plays an important role in quantum algorithms. But we won't. Okay, not going to get into that. What we are going to talk about is signal processing, and we're just going to get a sense of some of the concepts that are involved in signal processing. And so the presentation here is taken pretty much out of chapter 10 of your book. So I hope you guys will be able to follow along. And the way that we'll do this is I'm just going to give you some ideas, some concepts, just the general broad brush of what signal processing entails. And then there's going to be some demos that we'll do in between, some kind of hands-on things where you can get a sense of these concepts. All right, so first, just the basic ideas. So what is a signal? I mean, this is something that we're all intuitively very familiar with. But if we wanted to write down a definition, a signal is some time-varying or spatial-varying set of data. And if you think about like an example of a signal, if I have a flashlight and maybe I'm shining it at you, and maybe we're using Morse code or something, that would be one example of a signal. But in general, it could be anything that we can represent with a function f, and it depends on t. Right? So this would be a time-dependent function, and f is like the amount of signal that you have at a given moment in time. All right? But you could also have a spatial varying signal, which would look something like this, where now you have three coordinates x, y, and z, and then this would give you the amount of signal at any point in space. Right? Yeah?
Example, that might be what they do when they stand out on the boat and have the flags, and they do the various signaling.
Yes.
That has everyone is a letter, and you can spell things out.
Yeah, exactly. That would be.
Because there, the position of the hands are at least x, y, if not.
Yeah, actually, that could be a little bit of both, right? Because there's a time ordering of it as well, right? And so you need to understand the positioning also in the order of it as well. So that's a mixture of both the spatial and time varying. Yes. Yeah, exactly. Another example of just this would be if you were trying to look at if you had some sort of map, and f would be maybe the elevation at a given point in space, right? So that would be a way that you could represent. That would be a type of signal. It would be like the elevation signal. Or you could have color as well. So if you look at a picture, x and y would be like the coordinates on the picture, and then f could be maybe the frequency of the color being reflected. So those are just examples of signals. But the first take-home message is that we deal with signals ubiquitously. Everywhere we go, we have some sort of signal that we can represent in this manner.
Is a CD-ROM the information on it considered a signal?
Right. So the information itself, when the way that it's read onto your computer, that's using signals. So basically, there's a light that gets shined on the CD, and it has a particular diffraction pattern, and that diffraction pattern is a signal that's then sending information to your optical drive head.
Information is stored on the CD.
Yes.
X, Y coordinates, and then
it's read.
Dimple or flat, right?
Yep. Exactly. Okay, so we can characterize signals in two different ways of either being periodic or aperiodic. And here's the first one on the left is like an aperiodic signal. And this is sort of intuitive. What this means is that periodic means that you start at one point and you come back to the same waveform at another point along the x-axis. Right, so here the way that this just peaks here and then it drops off, decays, till t goes to infinity on both directions. So there's really no repetition here, right? It just has this one peak and that's it. Mm-hmm. Whereas on the one on the right, there's repetition. You see that I go up, down, up, and then I repeat the same behavior. Okay. So this idea of a periodic function is crucial in understanding signal processing. But intuitively, it's very simple. It's just something that repeats itself. And so why is this repetition important for signals? Because it reminds us of something that we learned in geometry class. Okay? So we're not going to get too deep in the math here, but it's important just to understand a few concepts. And I'm sure at some point all of you guys, if maybe you're teaching this in class, if you're teaching trig or something where you're drawing out sine and cosine functions, yep. Right, like this. Okay, so this is a periodic function, and here's the basic components to a sinusoidal function. You have a, which is the amplitude, right? And the amplitude tells you basically how high your wave is going and how low it's going. Right? So in this example, your amplitude is 1. Why? Because the peak goes up to 1 and it goes down to -1. Okay? So that's a amplitude. That's fairly intuitive to understand. So inside this parentheses here, this is basically telling you how the shape behaves as you move along the x-axis. So this omega here, which looks kind of like a W, this is called the frequency. Okay? And what the frequency tells you, this is a really important quantity. This is telling you how many repetitions you're making or how many cycles you're making per second. Okay? So if you look here, so here's t. So we start here, I guess if this is like at roughly -6. Okay? And then it gets back here 6, right? So in total, it took about 12 seconds to make one cycle. Right? Yep. Okay. So that would give then 1 over 12. So in one cycle per 12 seconds would be the frequency. All right, and then there's this other quantity here. This is phi. This is known as your phase. Okay, and the way to think about what this phase is doing is it's going to take this waveform, it's going to shift it left and right on the t-axis. So here, this is a picture taken from the book, which shows two sinusoidal waves, which have the same amplitude and same frequency, but they have a different phase. And you see, then all that the phase does is it just takes it and shifts it by this amount theta. Okay, I remember when learning about these. And it's something, I don't know what grade it was I learned about it, but everything kind of just makes sense because you get a nice satisfactory feeling of drawing this out and seeing, okay, A goes up like this, and you can actually measure the frequency and you can look at the phase shift all just by looking at the graph. So this is a really nice connection between the algebraic expression of your sine function and then the graphical depiction of it. Okay. So, and these are what I say here, these are the building blocks because really this is how we're going to understand periodic functions in terms of these sinusoidal functions, general periodic functions. Okay, so let's take a quick break and let's do this activity. So this is pulled right from your book. If you guys want to think about this for a minute. Let's see, it's a little hanging over the edge there. But so here we have three functions, or sorry, two functions, f1 and f2. And oh, by the way, let me just point something out. So here you see that I wrote this in terms of sine, right? But you can translate sine into cosine just by if phi here is 90 degrees, if the phase shift, then it translates the sine function to the cosine function. So really we could have written cosine here and it would have been the same. It's just choosing a different phase. So here in this activity, the periodic functions are given in terms of cosine. So let's think about this. So the question is which graphs represent f1 and f2 and which cannot be either. So first let's go here. You guys want to just think about this for a minute? It's in your book too if it's difficult to focus. Right, so I heard f1. What's your reasoning?
The amplitude is 5.
Yeah. Yeah.
Instead of repeating every pi, it repeats every pi over 2. And 2 times pi over 2 would mean it repeats every pi. So the period is pi over 2.
Well, let's see
And
here.
the period of a cosine wave should be pi.
No, it can't be the first one because the second and third one both have the same frequency. So it has to be the second and third ones for the equations we have.
Okay. So, well, you're assuming that we don't have repeats, right? Yeah, but right. Okay, so I mean, okay. So let's put it together. I think among all the comments, I think you guys have come up with a solution.
My math's weak.
Right.
It should be 2 pi instead of pi, so
Right, and
pi is all the way around the circle, not pi.
yes. So
I misinterpreted what the period should be.
yeah, no, it's no problem.
It should be 2 pi, not pi. So
Right. So
here has a period. The green one should be 1, F1.
yeah, this is 1. This is F1.
Period of pi instead of a period of 2 pi.
That's right. So let's I'll state this again another way. So if you go from 0 to 2 pi, it would just be cosine of t. That's the period of just cosine of t. But now if we look as we go from 0 to pi, let's count how many times we repeat the cycle. 1, 2, 3. Right? So the frequency is 3 times as much as cosine t. Right? So what we would expect, for this, we would need to have a coefficient of 3 here, of t, right? Because we did 3 cycles. 1, 2, 3. So there's no 3 there, so it's neither of those. This one, okay, so this one, we can eliminate F1 immediately because the amplitude is 10, right? So now we just check the period. And so now we have 1 cycle, 2 cycles, and 2 pi. Good, so our frequency is correct. And then this one here, with 1, 2, so frequency is 2, amplitude is 5. Good. Okay. Let's do another one. Should think about this for a minute. All right, how about this one? So first, what's our amplitude here? Amplitude is 10, very good. Okay, both those are 10, so that really doesn't help us differentiate. That's right. Now the frequency, so let's count. 1, 2, so in 2 pi we went twice. So that looks like our waveform there, F2. All right, 5, okay, doesn't even, this is a neither. We can just check though, the period is right? The period is 2, but the amplitude is 5. And then this final one, amplitude is 10, and in 2 pi we make 1 cycle. So the frequency is 1. Okay. Make sense? Good. Okay. So the next idea we need is something that, again, is very intuitive. It's this idea of wave interference. Okay. So suppose that you have 2 sine functions here. So here's sine pi t, here's sine 2 pi t. And I'm going to draw the graphs together. All right, so this is, I guess this was orange or maybe it was yellow, but this is the sine 2 pi t, and the blue is sine pi t. Okay, so I've taken these two functions and I've graphed them simultaneously on the line. All right. Okay. Well, then what we can say is, well, actually, what if we added these together? All right, now when you add together graphs, the way that you do this, it's you pick one point on the x-axis here, and so I add the blue point to the orange point. Right? So if I pick the point here, I'd add this point with that point, and then that's going to give a new graph. Right? It's going to give a new waveform that looks like this. All right? So this is the wave of sine pi t plus sine 2 pi t. Okay, and so this is known as wave interference because you're taking these 2 waves and you're interfering them in a way to give you a new wave. And just something to note here is you see where this hits the x-axis here. This is where y is equal to 0. So there's 0 wave here. So that's known as completely destructive interference. Right? That means that you had it would correspond to something like here where the high wave crest interferes with the low wave crest in the other one, and they completely cancel each other out.
And that's how you get the flat line?
That's where you get what's with 0 here.
0.
Yes.
Okay.
And on the other hand, this is where you would have a spike. This would be constructive interference. You see the amplitude here is above 1.5. Whereas each of these guys, individually, they're combined to 1. Right? So when you combine these things, you get a wave of greater amplitude. It's higher than 1. So that's constructive interference. Okay, again, something we're really familiar with, just if you go to the beach and you watch waves collide and you see shadows out in the water, that's all interference effects. Something to notice here is that this function itself is periodic. Right? It doesn't look like a sine function, but in fact it is periodic, because you see you start, there's one cycle, and then it would repeat again. Right? So it's not obvious, but in fact, if you just carefully look at it, it's a periodic function. And so what we observe here is that when we add two periodic functions together, we get another periodic function. Okay? Now, is this a coincidence? Well, the general rule is the following, that if you have two signals, say f1 and f2, and if we divide their frequencies, okay, so divide omega 1 by omega 2, if it's a rational number, then f1 plus f2 will be periodic. Okay, so rational number, this is, if it's not, if you can't really remember what that means, all that means is that you can write it as a fraction. Okay? So if their frequencies is a fraction of, like, say, 3 over 5 or 2 over 10, then their sum will be periodic. So here I give an example of this. So if you look at adding these guys, so here's one wave, here's another one. And so the frequency here is 1, and the frequency here is 3/2. Right? And so now if we look at this rule, if we divide 1 over 3/2, that's a rational number. That's 2/3, which is rational. So now, and in fact, if you can see this is definitely a periodic function. You can see the repetition. Okay. On the other hand, here we add two waves. So here the frequency is square root of 2 on this cosine, and here it's 3/2. So square root of 2 is an irrational number. It's a non-rational number. So if we look at this ratio, it's not rational. And in fact, this is aperiodic. Now you look at it and you might say, well, this looks fairly periodic to me. Right? It kind of looks like it's doing the same thing, but actually it's not. If you observe what's happening, the frequency is getting smaller and smaller. So the time it takes to go on one cycle is actually getting shorter as t gets bigger. So this is not a periodic function. Okay, and again, the reason is that if we look at the ratio of the frequencies, it's an irrational number. Okay. So a really nice application of this is something known as harmonics. All right, so do we have any musicians here? Yeah, very good. So you've probably heard of this term harmonics. What instrument do you play?
I play multiple instruments.
Okay, very good. Well, almost all instruments use this. In fact, all instruments do use this idea of harmonics. And harmonics are what gives different instruments their unique sound. And so the idea is the following, is that you start off with some, which we call a fundamental frequency. So here's like some baseline frequency. And now we take integer multiples of that frequency and we construct the waves. Right? So here this has a frequency of twice the fundamental one. Here's 3 times. Here's 4 times. Okay? So we can build up all these different, what are known as harmonics. All right? And they're all obtained by taking one initial wave and then doubling the frequency, tripling the frequency, 4 times the frequency, and building up a collection of waves here. All right? And then what we're going to do is we're going to interfere these guys. So we interfere the harmonics. And that'll give us a new wave. And depending on the amplitudes of the individual harmonics, it's going to produce a unique sound. Okay? So this is actually how instruments differ, is that they differ in the amount of harmonics they have at a given frequency. So let's look at this in a bit more detail. So here's an idea. So here we have just sine pi t, and here's so this would be like your fundamental frequency of 1, and then here's your second harmonic here because the frequency is twice as fast. Okay, so you have something that looks like this. All right. Now we can add these two together, and we would get something that looks like this blue curve here. Okay? So here we're just adding these guys, and the amplitudes are the same. It's F1 plus F2, and we're getting some new wave here. This is a combination of the first and second harmonics. But we also have the ability to change the amplitude of the individual harmonics. Right, so here what we're going to do is we're going to take the first harmonics 3 times as much, and we're going to take the second harmonic -2 times as much. So this -2 just means that it's going to flip the wave. Okay? But the point is that we're using these individual harmonics as building blocks. Okay? Mathematically, we describe these as taking linear combinations of the harmonics. And what you get now is when we add this 3 sine pi t minus 2 sine 2 pi t, we get a different wave. Right? So the main idea here, by changing the amplitudes of the harmonics, we can obtain different interference patterns. All right? So just using these two functions as building blocks, we can create a whole bunch of new functions by changing the individual amplitudes and then interfering them. Okay, so this is a really deep idea because, in fact, what's remarkable is that any periodic signal can be decomposed into a sum of harmonics with different amplitudes. Okay, let me just kind of back this up again. So basically, this orange curve, what do we know about this orange curve? We know that if you just looked at it, it's not obvious, but in fact, you can write it as a sum of the first and second harmonics. You have to scale the first one by 3 and the second one by -2. So we're decomposing it into individual harmonics. Okay, and so then that begs the question if any function can be decomposed in this way. Right? If you give me any periodic function, can I always write it as a particular sum of the harmonics? And in fact, this is true. And this is what is known as a Fourier series. So what a Fourier series is it takes some periodic function and then it breaks it down into an interference of the individual harmonics. Okay, so here's an example of this. This is taken from the book. So this is a square wave. Okay, so this is about as boring of a periodic function as you can get. It's flat, drops down, right? So this is just going to go on forever. Okay, and so now what the Fourier series theorem says is that in fact we can think of this as actually being an interference pattern of different sinusoidal functions. And so here it is. If you look over here, I've graphed 3 functions, sine pi t, sine 3 pi t, and sine 5 pi t. So this is 3 times the fundamental frequency, 5 times the fundamental frequency. So the first one is the blue curve. The second one is the orange curve, right? That has 3 times the frequency, and then 5 times the frequency is the green one. See, it's going fast, exactly. Okay, so now look what happens. So now if we add these functions, if we associate some weight with them, so I multiply the first one, the amplitude, by 1, the second one by 1/3, and the third one by 1/5, we get this resulting wave. Right? And it's fantastic, actually, that something that looks nothing like a sine wave can actually be made approximately by taking combinations of sine waves. Now here we just took 3 harmonics, but what the Fourier series does is it would actually take an infinite number of harmonics. And so the idea is that we would add more. So we go F4, F5, we'd add more and more, and mathematically this is what you do, and you get something that approaches the shape of the square wave more and more. Okay, any questions on this?
Are you able to go back to, I have a question.
Yeah.
Go back that one.
Yeah.
Okay, so when you know how we talked about when you change the amplitude, so 1 is 3 times and 1 is a minus, because
Yeah.
the A is a negative, like a -1, but it's -2.
Yes.
When we flipped, did we, because usually like when you flip it's over the X, or then you flip over Y.
This is over the x.
Thank you.
Yep, exactly.
Okay.
All right, so now the fact that we can write a periodic function in terms of these harmonics allows us to interpret a signal in a different way. This is the idea of a frequency domain. So the idea is that what we'll do is we'll take our signal and we'll store it as a collection of sinusoids. Okay? And this is the basic idea of data compression. And we're going to get to the lab here to where you'll see this. So the idea is that instead of storing the amplitude of the signal at each moment in time, we store the amplitude of the harmonics constituting the signal. Okay? So let that kind of sink in. Instead of storing the amplitude of the signal at each moment in time, we store the amplitude of the harmonic constituting the signal. So to go back to our sine wave, so instead, imagine if you were to try to describe to someone the sine wave function. Okay? So one way you could do it, and this would be an inefficient way, but you could write down at every single moment in time, you could write down the value of the signal. Right? That would be a huge list. A more efficient way would be if you just wrote down the coefficients 1, 1/3, and 1/5. Right? With 3 numbers, now this is not exactly the square wave, right? It's something that looks similar to it. But with 3 numbers, we're able to approximate this function pretty well, right? I mean, yeah. I mean, and we'd have more numbers. The more harmonics we add, the more we'd have to add to the list.
But either 1, 3, and 5 also, or no?
No. So once you define your fundamental frequency, then you're good. Just the amplitudes.
I could see this working for sound, but will this also work for like pictures?
It will. Yep. Yeah.
'Cause what's the sine waves for a picture?
Well, so it would just be, I mean, formally all you're doing is you're just changing from t to, let's just say x or y. Okay? Okay. And so then the idea is that we express the amplitude of the harmonic with frequency omega as a function. Okay, so what this function g omega is doing is for every harmonic frequency omega, it's going to give you the amplitude. And this is called the Fourier transform of this signal. Okay, so to our sine wave example, so here's the Fourier transform. It's actually a very boring function because remember, all we needed were 3 points. We just needed 1, 1/3, and 1/5. This is what's known as a discrete function here because we just have a discrete number of frequencies. So basically what you do is you look up your frequency on the x-axis, and then on the y-axis here, that's the associated amplitude. So here the frequency is pi, right? So 1 pi, so I go here. What's the coefficient there? It's 1. So I put a check mark there. Here it's 3 pi. What's the frequency? 1/3. So I go to 3. It's 1/3. Right? This is just the Fourier transform of that. So for periodic functions, its Fourier transform is discrete. Again, discrete means that these lines aren't connected. They're just dots. Right? Because I just have a discrete number of terms here in the series. However, for aperiodic functions, we can also define a Fourier transform. Right? And it's the same thing. It's just a function of omega. But now this is a continuous function. Okay, so for periodic functions, your Fourier transform is discrete. For aperiodic functions, your Fourier transform is a continuous function in frequency. So here's an example, and we're gonna break it in just a second here. But this is what you guys will be doing. So here is the signal of a whistle. All right, and you're going to be doing exactly this in a second. So you're going to whistle into the microphone, and what it's doing is this amplitude per second. Okay, so here is what's known as the time domain. So this is like your f of t here, and here is the Fourier transform of that signal. And this is actually, it's close. I mean, it's not a truly periodic function. This is slightly aperiodic. The amount of time to go from one cycle is not the same, so it's not quite aperiodic. And that's why here you have a peak around the frequency, which is the approximate frequency here, but you have a little bit of shifting as well, right? Because this is not entirely periodic. So this is taking it's giving you the amplitude at a given frequency. Okay, so let's actually do this so you guys can see this in practice. In your lab kit, you have this microphone headphone set. Okay, now on the desktop, there's a folder, and you can look at the screen here. There's a folder called Lab View. I'm sure everyone has that. Oh, yeah, maybe warm up the computers. Sorry.
We have to log in. So the login is EWSES321. All right, on board.
Oh, okay, thanks. All lowercase. It's case sensitive.
All works. One. Do you have a switcher? Either that or you're already looking like the student.
Okay. Now, once you're logged in, wait, before you plug in, there's an order of operations here.
Uh-oh.
Yeah, because if you do it, you have to load the program first before you plug in. It is okay. So there's a Lab View folder here, and then it's called Spectrum Voice.
Yeah, there's an old one and a new one, so use the one in the bottom corner.
Oh, the one on the bottom?
Sorry, bottom right corner. All the way to the right. Or, yes, your desktop is there.
Here,
Yes, not to the right, they're both actually lined up.
let me see the contents.
I can
Yeah.
see,
This one it says old.
this is 7.
Current, maybe open that.
It says the current version.
Yeah. Just do the current one. Okay, and then it's Spectrum Voice.
The new one.
Okay, and then plug in the your headphone jack into the headphone port on the front of the computer, and you should get a little Dell. What was the device again?
It should be,
No,
it should just be headset.
headset. Just click on headset. So okay.
Well, it says earbuds.
Yeah. Let's see if that works.
And it gives you options, so which one do you want to do?
Where do you choose headset?
When you plugged it in?
May or may not have done that.
Yeah, it might not.
Oh, yes.
Okay, and the activity we're doing is on page 96. So I'll let you guys read over that. There's actually two things you're going to be doing. You'll be whistling and weeing, screeching.
When do we start getting signal?
There's a play button
Oh, okay, thank you.
right there. And the mic.
I see pause, abort, run, I see a run.
Right there.
Okay,
And now. Yeah, so now it's recording.
okay.
So we have to plug this first, so we have to launch the program. Oh, okay.
The time domain's on the right, is the left the Fourier Transform?
I
Yes.
see run. Is run the play button?
Yes. So try to get your whistle as periodic as possible, and you'll notice you'll get a spike in the frequency domain.
me just picking up everybody else.
Is it?
It's picking her up.
Oh, I'm sorry, she was on. Ooh, it's not good when it does it back.
I can get it on the.
Which one?
Yeah, I don't wanna have it in my ear when I do, because it's real high.
Oh, sure. You know what you can do? You can also turn it down, down there. Yeah, I know that's kind of annoying.
It's very loud.
So that will turn it down.
And that's the thing, is if you do certain whistling, it does get the harmonics, and then you get the higher pitch back.
Yeah. Okay.
So
Okay.
you, sometimes people do something and it's very high pitched, and
Yeah.
then it goes back, that's that higher harmonics that they hear, not everybody hears it, so.
Do you have a question for whistling while you work? Oh yeah. That's
You
one
know
thing.
what I really wanna do? Can I do it?
Go ahead. Oh, okay, you need to come over here with
Yeah.
that.
What does that look like?
Ready? It's really fascinating, actually. This is
I
great.
can do that. But
We gotta have you come up to the front.
Yeah.
and do
Can
it
would
so
you mind
that
doing it?
recording-
Yeah, we can see
Can we see it?
It's tight, it's tight, it makes it, it's a pure.
Yeah.
But you know what I wanna see it do when it's straight tone and then versus the vibrato.
Okay.
That's the
Yeah.
frequency of Fourier.
Okay, okay.
This is the time of sleep, that should look like the same.
So,
That's really good.
Going off the scale. 2,000, 4,000. Let me make an adjustment so that we can see the higher.
We want to enlarge it too.
Okay, so let me start this. I don't think you're gonna get that high, but you may as well, actually it is. Okay. May as well see it.
Oh, wow.
Wow. No, it's good. It's up to 20,000. Okay, let's see if I can.
Yeah.
Very good.
Mm-hmm.
this would be an interesting project to do with students based on their voices and their pitches, right?
Mhm.
And then see, when they talk certain ways, if people listen to them more.
Yep. That's true.
That was gonna be harder to.
Or how well they're screaming at
How do
On
the
the
we-
show, right?
Yeah. The person right next to
I
them,
agree.
yell at the screaming.
So I'm gonna try something. I'm gonna program on the spot. I'm gonna see if I
Thank
can
you.
at least
That
move
was
the
great.
dominant frequency.
Yeah, no.
That may or may not be a good idea.
Oh, I took the photo.
And if you do the, if we sing harmony, then that's gonna even change what it looks like.
What do I do?
So, this was just a do, mi, do,
Me. Me.
Let's do another one. You do do,
Do.
mi, so. Keep it.
Oh. Do, re, mi.
No, just stay with do.
Do.
Mi, so. Just picking other people's stuff up.
Mm-hmm.
Can you do the harmonies again?
Right? Do. You do do.
Do.
Yeah, that's great. You can just see just the piece.
Mm-hmm.
Yeah. That's really cool.
And there's filters, right?
Yeah.
So.
Close enough. So I'll figure out how to, so based on that, Erica, I'm gonna figure out how, so that I can tell us what the exact frequency of the peak is. So I almost have it, like I have the number, it's the 24th element in the array, but I need to convert that to what frequency that corresponds to, so that different singers can hear like what frequency they're actually hitting.
Right, they have something they connect
Yeah.
it.
So,
Add it right on.
it's something that I'll add.
Okay, sounds good.
Okay, so
So can we talk about,
yeah,
is this a capture of, this is a capture of her voice, of her, is this a capture of her voice?
No, this was
Cell phone apps.
something else.
You were not able to, were you able to capture it and save it?
Can we
This
do
would
it
be a
again?
good discussion.
Can we do it again and then I'll?
Yeah, but you know what I'm curious is, okay, so like when you're a singer, right, or instrumentals, you have a pitch, right, and you think of pitch a certain way, right? So if you're working with a accompanist, they're like, oh, you've got to be on the piano at this, right? So what is actually the frequency the piano is versus the frequency of the same pitch that the voice is? That's what I would think is interesting.
So
Because that would, they would be different, just because it's the same pitch on the different instruments, it's gonna be a different frequency. So what you're saying, what I like what you're saying.
well, so what I may or may not have understood it fully. So when you sing, you typically generate multiple harmonics.
Right.
And when you play piano, it may also generate multiple harmonics. So
Right.
if everyone's in key, it should hit the same exact frequency.
Right, and then
But like the amplitudes of the different harmonics may be different
Different,
for
right.
the different tunes.
Mhm.
So is your question to figure out, can we check to see that people are on key, that they're
Well, you
at the
can,
same
because you can
frequency?
hear it.
You can hear it.
You can hear it,
And
but
then-
I'm sure you can see it then on here.
Yeah,
Oh,
so we
yeah.
can, okay, so I'll look at how we can modify it to line these things
Yeah,
up.
because like musicians, like especially when you're working with vocalists, it's easier to hear it when you're working with vocalists. So when you're perfectly in tune with a group of people, like say singing 4-part, you can hear the lower harmonic,
Okay.
but you could be perfectly in tune. So that's, anyway.
actually that would be cool if you could have a tuning like thing where you
Like
show
your
someone goes a
off.
little flat a little bit and you can
Yeah.
see
Well,
the
and they have that, I mean, when you, like, they're called, they're like tuners, and so they're, you know, you can put them on your guitar, you can use them for your violin, and it shows you what the pitch is.
There's cell phone apps too, aren't there?
Yeah.
Yeah.
so-
There, I'm sure there are, I don't use the cell phone apps, but we use the outside tuners.
yeah.
It's gonna capture that, I wanna see.
Oh, it's a capture and record?
Yep.
All right, so
Are you
we'll
able to
save
capture
yours
and
as the
record?
default, so go ahead and do it again on this one.
All right.
And I'll save it as this file.
Alright.
And we have to decide at the exact moment that we want to save. 'Cause we
Okay.
can save one moment. When you're ready.
That was a little different than before.
So this one, do we want to save this one?
You wanna do
That's
it
the
again?
default.
What do you
Yeah,
want
because it's
longer?
like, the last time you went, you kinda like carried it out, this one
Oh,
you just
okay,
went
no.
coast
Oh,
up.
okay.
Yeah, sorry. And my voice goes, I'm just kidding.
All right.
There you go. Okay.
I think I captured the same thing. Looks similar.
Well, there's the same pitch, I'm
The
saying
same
the same
pitch,
pitch.
okay.
Right, it was just the ending, I think the way you went, you kinda like moved out versus you just stopped almost cold turkey.
Yeah, so
In
this
twin
will,
breaths.
this is basically one pitch, and so, with this data, I can actually reload it and have it play back at this pitch initially. I'll adjust the volume.
That's good. Thank you.
Nice.
Mhm.
Yeah, thank you.
That was good.
I get 10%.
There we go.
But okay, so this is now. I mean, this is you can kind of see how a data compression idea would work because, first of all, if you just look at this, on the right you have all these lines, right? So this is like a whole bunch of data here potentially, but on the left it's pretty much black except you have these peaks here, right? So you can just intuitively guess which would require less memory to save, this or this. Right? So the idea is that with data compression, you just need to store the information of the individual peaks there. Yeah. Okay.
That's what you were talking about, the discrete points that you.
Yep. Yeah. Yeah. So I mean, and with this example, it's quite dramatic because I mean, you were just singing one pitch, right? And so it was fixed. If you think about a song or a conversation, it's much more complicated than that because we're not speaking at a single pitch. We have dynamics and we have different enunciations. So all of that has to go into a data compression algorithm. And so we all have familiarity with these, with whether it's your iTunes or MP3. These are all technologies that are employing these concepts into the audio compression. And so we're going to actually look at now a more realistic type of compression, not where it's not just at a single pitch, but on an actual song. And if you open up in that folder, audio compression tones. All right. And so now this is going to be a compression tool for the Illini Fight song. And so on 98, you can just read on the activity of what you'll be doing. Linford, is there a compressed?
Second. So if you run.
So that's running the original. But is there a way to?
So you're through.
Okay. Gotcha. That's just pressing this one. Yeah, good. Got it. Yeah.
You want me to change this factor now? And push back?
Yes. So you hear it, right? The original.
Yep.
And you can change the compression factor, and then you can also change the number of sinusoids it uses. So basically, that's the number of peaks that it's. So it's going to count the 25 peaks. So it's going to store that data, and as you decrease the number of sinusoids, it's going to basically save less and less data, so that you would expect the sound to deteriorate.
And you heard what it sounds like.
Okay.
So, yeah, go ahead and respond.
Okay.
So that's what it sounds like when it's compressed.
Oh.
Change. So look here, change the numbers.
Right here?
Yep.
Okay.
Go more or less to see.
Okay.
Yeah, run it.
Okay.
Hit the close.
Bad.
Is yours working? Okay, so, stop this one. Stop.
change the compression factor.
And see, does it sound
That
correct?
sounds horrible. Yeah, it sounds terrible, right?
Were you able to do compressed?
Yeah.
Okay. You got one? You got yours?
Yeah.
Okay.
Sometimes when you're on a budget, you gotta make cuts.
Stop that.
That sounds good.
You getting it?
The 25 isn't
No. He's even trying it down, just start off with 4,096.
So higher it is, the better it sounds.
Yeah, because you're basically taking more sinusoids.
Oh, okay, yeah.
What's typical for like an MP3? And then, we have
Typical MP3 compressions.
Question.
Yeah.
So typically you can compress, so like an MP3 is like 4 or 5 megs, and the original file is like 300, so it's about 100x compression ratio. So I think with 44,000, it'll probably use 400. So if you go from 44,000,
we're looking at 81.92 compression factor ratio, and it's, you can tell the difference. So an MP3 really does give the best quality.
my numbers are approximate. Maybe it uses more than, so I originally came up with 400 sinusoids.
400.
Yeah, because this is, so this is, I think also the original number of sound samples matters. Like it's, I think it has to do with like how the blocks are processed, like how chunky it is.
In standard MP3?
Yeah.
Yeah.
Compression ratio and typical MP3 audio
11 to 1. Oh, but here, okay, so, yeah, so the original rate is 1.4 megabit per second. Oh, wait, no, here it is, 44,000 samples per second. And so
Two
instead,
channels 'cause it's stereo.
yeah, and so instead it goes to 128 samples per second. Or no, 128 per second. I don't say what the sampling is. So the sampling should be the same, it's just the number of sinusoids should use.
Okay, I think we're just going to move on to just keep things on schedule. I have modulation I was going to talk about. Or,
Okay, go for it.
yeah. So one more concept in this introduction here is this idea of modulation, and sorry. Yeah. This is just a conceptual thing. So so let's go back to our standard form of the signal with this function f of t. And so what modulation means is what you allow is the amplitude to also be a time-dependent function. Okay? And so then what this does is you can basically take your sine wave and contain it in what's known as an envelope. So here, if a of t was a linear envelope, so a of t would be t, so this would be a line there, or you could have a parabola, t squared. And let's see, and so basically here's an example of a linear modulated signal. You see, because it's periodic, but the amplitude is getting smaller, right? And then it's getting larger here. And we can contain the entire signal using a line. This is x equals y, and x equals minus y there, right? So we're basically putting the original signal in what's known as an envelope. Here it's a linear envelope. And this is known as modulation. OK, so here's the plots with cosine t, and then we scale the amplitude by t. All right? So this is just another concept that in signal processing that's used, this idea of modulation. OK, I think that's pretty much what I wanted to say.
What's the purpose of modulation?
It's, well, let me think.
I mean, later in the term, you're going to be doing frequency modulation and amplitude modulation. So we're mostly interested in understanding how
We're
does
storing
data.
broadcast signals and
Yeah, I mean, basically we want to understand how does a data signal that's being transmitted by the FM transmitter, what does it look like in the time domain?
because you're modulating the frequency.
Or if you have amplitude,
Amplitude, right.
it's
It's
going to
in
look
the
like
Yeah.
time domain.
AM and FM. This is how AM and FM signals are generated.
And you can also, yeah, so this also gives you, I guess, one way that I think of it as well is it's an extra degree of freedom for storing information. Because now you can modulate the amplitude as well, and that can be a way to transmit information.
Carrier wave, and I want to store a radio signal on it.
Right. In fact, what you can do is you can have this, the modular, the envelope also will have can have some carrier frequency as well. So you can have the envelope be a wave or resemble a wave itself, and so then in that envelope you can store information. Yeah. Okay. Good. So that's, I think, the end.